Good afternoon to everyone. This session will be handled by Dr. S. Sundaram in the title of Introduction to CFD and Fluent. He is working as assistant professor in the Department of Mechanical Engineering, NIT-PUDHUCHEERY. Our session is over to you, sir.
Thank you. Good afternoon to everyone. Please wait, we'll still share the screen. Share this. Whether it is in, I think you have to share it to make it full screen and then share it. Otherwise, they will not be able to see it. The screen is visible. Online participants. So the screen. Are you able to see the full screen? No response in chats. You can raise your hand if you want, if you're able to see the screen. Yes, okay, so the screens are visible. Okay, it's in presentation mode, isn't it? Is the screen available in presentation mode? Yes, okay, good. Thank you. Okay, so now, again, I will welcome you all for this session on computational fluid dynamics. I hope this session is going to be on basics, fundamentals, and what is a CFD, and mainly concentrating on how Ansys is working in the background. Okay, so that's going to be the main session. So if you're already having expertise in CFD, we'll be looking at the basics and maybe a little bit on what is the new frontiers of CFD. For those who are looking at it the first time, I think it will be a session where you can look at how to work on CFD. So that's the general idea. Okay, so now, okay. Okay, so computational fluid dynamics. So what is computational fluid dynamics? With the development of computers, we were able to solve high-end mathematical equations which were not being able to solve beforehand. So when you're going to look at the Navier-Stokes equations or the ordinary differential equations, they were very much long. You could solve it by hand or the other way. So now, with the help of the nonlinear equations, which were unable to be solved by hand, was able to solve because the computation time is going to be much higher when you're going to do it with hand. So with the development of computers, we are able to solve these fluid dynamics problems. So we will be able to solve an airflow over an hypersonic aircraft at Mach 7. So we can find what will be the pressure and temperature, velocity at different locations. To do this in hand, we will not be able to do it. Otherwise, it will take very long time to do the same thing. So that is the advantage of using computational fluid dynamics. And generally, CFD, when it was introduced, was called as a colorful fluid dynamics. The major reason is because we will be able to give results like this with color plots and other things. So traditional experimentalists, they were always claiming CFD was colorful fluid dynamics. You are just giving some results in color. But with the inventions in experimentation, so we have players, other OH chemiluminescence, thermographies. Experiments are also now going to give with colorful results. The experiments results are no longer in XY plots. We are having colorful plots, some images, multiple things we can get with colorful images. So that being the sense, the present terminology for CFD is click fluid dynamics. You are clicking something and the results are coming out and then you are going to talk about it. People must know what is being done behind the screens of any software which you are going to use. Okay, so that is essential because otherwise what's going to happen is we are assuming something and then we are not sure of what is the reason for selecting some particular property or parameter. So that is essential. So we will be looking at how to select various properties and what is the reason for selecting these properties in this session. Okay, so generally when you're going to have a problem, the problem can be achieved in analyzed in various methods. Traditionally, we were having experimental methods. So you have some pipe, and if you want to look at the various pressure and velocity relation, you can do some experiments on it, and then you can find a value for it. And then you find a relation between the parameters which you have considered. So that's going to be in experimental methods. And then you can also have the mathematical modeling. You can start writing equations for it. So you are saying that pressure is going to be velocity is going to depend on pressure. And then you develop an equation, you will get our Bernoulli's equation. If you're going to introduce viscous, then we get other equations. So that was the general thing. So, but the problem is the mathematical modeling will be coming in partial differential equations or ordinary differential equations, which will not give the same answer as that of the experimental methods. So what is the difficulty in it? The thing is, experimental methods are going to have include multiple parameters, and mathematical modeling, we are going to make some large of assumptions. We are going to assume the flow to be one-dimensional, steady, inviscid. All those assumptions we are making. The thing is, we are making those assumptions because then only we'll be able to solve it. So if we are going to reduce the assumptions, and then if you are going to solve the basic mathematics, that becomes our yes, numerical simulation. So the thing is, we are going to use the help of CFD. So now what we are going to do is we are going to discretize the experimental domain into small segments and then apply the mathematical equations in these small segments where the assumptions are going to be still valid, and then we are going to look at the results. So numerical simulations are going to be aiding the experimental methods and the mathematical modeling. And we also have to make sure the numerical simulations are not going to be 100% replicating what is going to be in the real life. Numerical simulation cannot replace standard experimental methods. The reason being, whatever we are going to do, still we are going to go with some mathematical equations, and that's going to be additional parameters which we could not have considered before we are going to do the experiments. So a classical example is, if you are going to say we are looking at flow inside a pipe, if you are going to say we are going to solve it with pressure and velocity terms alone, we are solving for the Bernoulli's equation. So that means we have neglected the effect of friction. But when I'm going to take a pipe and then if I'm going to do an experiment on it, if the pipe is not smooth, then friction effects will be coming into the picture. So that means my assumptions are wrong. So there should be an experimental to back it up. So that being said, these are the quotes from my guide, Professor V. Babu at IIT Madras. He would always say that what cannot be measured has to be modeled. Experiments cannot be used to measure all the parameters. So the thing is, when you're going to do an experiment, you are looking at you're fitting a pipe, but you will not be able to get the pressure data at each and every point in the pipe. If you're going to put that much number of pressure probes, the data collected will be very much huge, and even the pressure probes can disturb the flow in the first hand. So that means which cannot be measured has to be modeled. But at the same time, the saying goes, what cannot be modeled also has to be measured. So that means there are some limitations in our numerical modeling also. There are going to be some things which we cannot model. So if you're going to look in go whatever high-end computational facilities we are going to have, the computational system is not going to replicate what is going to happen in experiments. The turbulence phenomenon is going to be really high. So the thing is, what can happen is any small disturbance in the actual experiments we cannot be replicated in the numerical simulation because we are still going to go with some assumptions. So if our modeling is not correct, matching with the experimental data, we have to go with the experimental data always. So that's going to be the crucial one. Okay, so computational fluid dynamics is going to be broadly classified as finite difference method, where researchers who are mainly working on codes we'll be going for this finite difference method, and where you discretize a domain and then you take the properties at each and every point. So you can develop a method to calculate it. Or finite volume method, where you differentiate the domain into control volumes. So where you are interested in the mass flow and energy flow into the individual control volumes. And finite element method, where we are going to give weightages to the nodes. Finite element method is mainly concerned with structural analysis. For fluid flows, you'll be mainly going with the finite volume method, and commercial softwares like Ansys, OpenFOAM, StarCCM, where you're going to have the fluid flow, they'll be using the finite volume method. So we will be looking at the basics of finite volume and how it has been incorporated in the Ansys Fluent in this session. Okay. I will be taking references from both finite difference and finite volume as we go on this session. But finite element, we are not going to touch into it because that will be completely a structural problem. Okay, so now when you're going to have a domain, what we are going to do is we are going to divide this domain into multiple points. If you're going to divide into multiple points, and then if you're going to take the parameters like pressure, temperature, velocity at all these points, it becomes a finite difference method. On the other hand, if you're going to look at cells like this, where you're going to say fluid mass is going to enter and then mass is going to go out, energy is going to enter and go out, then it becomes a finite volume method. So what's the advantage of finite volume over finite difference? Is the finite volume will be allowing you for discontinuity. So if I'm having a flame, I'm having fuel and oxygen coming here, and then it's going to burn, and then it's going to come out as exhaust products. So finite difference will be looking at the properties at all these points. It says temperature is here, so what will be the temperature corresponding here? What is the mass of species? But and the flame has to be calculated. Flame is going to be given by n. So if you're going to take this particular cell, the energy coming in of the fuel and oxidizer is going to be converted into heat, and then exhaust gases will be taking some amount of energy. So energy coming in is going to be equal to the energy going out. But in finite difference, the temperature here it may be something around 30 degrees Celsius, but here it may be going to around 1000 degrees Celsius, or you can around 900 degrees Celsius. That's possible. So this stark or a strong difference in pressure or temperature will be we can manage in finite volume much more easier than in finite difference. That is the reason commercial softwares, if you are going to go with fluid flow problems, you'll be going with an finite volume method than with the finite difference method. It's not that finite difference will not be able to solve this. Finite difference also can solve this. But the amount of programming still required will be a little bit on the higher end. So we'll be mainly going with the finite volume method to calculate this. And when you're looking at gas dynamics, you have the shocks. For shocks, a supersonic flow, once it crosses a shock, it becomes a subsonic. The pressure is going to increase, velocity is going to decrease. So as this kind of discontinuity can be easily accommodated in the finite volume method, so we will be looking at the finite volume method. Okay. So this is going to be a general equation for our computer CFD. Any property that's going to come in, minus will be having a positive value, and going out is going to give a negative value. Anything that can be generated within this cell is going to be a positive value, and is going to be destroyed is going to be the negative value. This is going to be equal to the total change of property in the control volume at a given time. So now if you are going to take this, the property as mass, then it becomes the mass balance. Mass in minus mass out is going to be equal to change in mass of the control volume. Mass cannot be generated or destroyed as long we are not looking in the nuclear fission and fusion reactions. We are going to be mainly working on thermofluid problems. So we will be considering mass is going to be a standard property. And this is the unsteady equation. If the flow is steady, then the right-hand side becomes 0. You have mass in is equal to mass out. The same thing you can go with momentum balance. Impulse in minus impulse out must be equal to the rate of change of impulse the rate of change of impulse will be given as the force. So this is going to be the second equation, which is we are going to solve. So force balance is going to be done where we will take different parameters as the force. We can have pressure force, viscous force, surface tension, all those forces can be considered. And then energy balance, energy in minus energy out is going to be equal to the rate of change of energy. Okay, so now we have not looked at any generation and destruction term at all. We are assuming that for general thermofluids, we will not be looking at energy is not going to be created, mass is not going to be created. So you don't have this E equal to MC square equation at all. Then why we are having this generation and destruction term? Any guesses? In normal fluid flow problem, which parameter can have generation and destruction? Yes, you can put it in your chat box. Those are in online, those are in offline. Any guesses? Which parameter can be considered for generation, can have generation and destruction? Heat is a form of energy. The thing is, you are going to say, we are going to look in energy, heat in the form of combustion, then I have to look at the enthalpy. So that's not going to be coming into my picture. So that is just a transformation from one form to another. So that is, I have to include the heat energy as an input in some methods, whether the species is going to have some enthalpy and some other species will go out with some other different enthalpy. The enthalpy difference is going to be given in the form of heat, which will be coming to the temperature calculation. But it must be destroyed completely or generated. One has to know. Huh? Burning of food, again, we are going to say I'm going to have fuel and oxidizer coming in with certain enthalpy. It's going to burn. The exhaust products will be going with some other enthalpy. That's going to be a difference in enthalpy. The change in difference in enthalpy is going to be equal to the heat produced. The heat is going to be in the form of temperature. So that's going to be MCP delta T. So the thing is, I'm having that energy, I'm having enthalpy as input energy, enthalpy as output energy, and heat as another output energy. So enthalpy in must be equal to heat plus enthalpy out. I don't have somewhere it is going to be coming abruptly. So that is going to be destroyed completely. Any other inputs? So when we are looking at second law of thermodynamics, entropy generation. So now if you're going to, a parameter is going to be entropy, systems, some fluid is going to come in, it's going to come in some entropy, and then it's going to go out with some entropy. The disorder can be generated within the system also. Entropy cannot be destroyed. So our equation will be modified in such a way that entropy in minus out is going plus entropy generated must be equal to the change in entropy of the system. Similarly, if you're going to talk of exergy will be destroyed. So when you're going to write your equations accordingly, you can have different balances. Okay. So the unsteady mass balance, mass coming in, going out will be given in differential form like this. And this is for compressible flows. We are assuming density to be varying from point to point. So we are assuming density is not going to be a constant. So density is also going to be varying. If density is assumed to be a constant in incompressible flows, we can take density out of the equation. And the equation will be modified accordingly. Dou U by dou X, dou V by dou Y, dou W by dou Z is equal to 0. Momentum balance, we are, so instead of, we will be looking at U rho U, V rho U, and W rho U. And here we have the pressure terms.
Laser point, right? Instead of mouse cursor.
Yes, that can be done. Yes. So here we have the force system. We said change in impulse must be equal to the forces. So we have here I'm assuming the pressure forces and viscous forces and gravity force. So if you're going to include more forces, like if you want to include surface tension, then the equation must be modified accordingly. So in Ansys, what we are doing is, if you are going to go and click a single button of viscous, then what it does is it includes this term in our equation and then it's going to solve it. So these are the same equations which is going to be used in the Ansys software also. So, but when you're going to click that button, we must know which equations that's going to be selecting. And yes. Okay. So next we have the energy balance, steady flow energy equations. Heat and work and enthalpy, kinetic energy, potential energy is going to be equal to the change in control volume of energy of the control volume. So this is going to be the energy balance. We are going to solve for this also. Okay. So now the thing is, we can write heat energy in the form of temperature and work energy in the form of pressure and velocity or shear stress and velocity. Force into displacement is going to be the work. So we can relate it to the stress and the velocity. So now we have converted all these into our known properties. And so the parameters which we are considering are going to be. Okay, I forgot about the species balance. So when you're going to have chemical reactions or diffusion of species, we have multiple species coming into the picture. So you have the mass of individual species and the velocity in which they are going to move, how they are going to diffuse. So we can consider for individual species, the momentum and the continuity equations can be considered. So now this is going to be the equations and the unknowns we are going to have. So we have continuity equations, the mass balance. And in continuity equations, we have rho, U, V, and W. If it's going to be in compressible flow, three-dimensional compressible flow, we are having rho, we have rho of rho U by rho X. So all these are unknowns. We don't know that we must find the density, velocity in three directions at any particular point. When you're going to give Navier-Stokes equation, yes, we are going to have additional unknowns, the pressure. The thing is, what we have said is the shear stress can be written as mu into dou square u by dou x square or dou square u by dou y square. So that relation, so I can replace shear stress in terms of u, v, and w. So generally, I'm going to find u, v, and w only. So now I have additional terms. So when energy is going to be coming, I think we have a look at that. We are going to have an energy equation. Temperature is going to be coming. Q will be written in terms of T. And work is going to be written in terms of pressure and shear stress. Shear stress is going to be again written in terms of U, V, and W. And then you have individual species. So if I'm going to have N species, I have N individual mass. So now if I'm going to look at if I'm going to have air is a mixture of oxygen and nitrogen. So I must write mass fraction of oxygen, mass fraction of nitrogen. Then I can find the total mass of air, something like that. So if I'm going to go with two species, my equations are going to be, I have an equation for oxygen, I have an equation for nitrogen, and then I have one energy, three Navier-Stokes, and this. So if you're going to add it up, you're going to have 5 plus n equations. And these are going to be your unknowns. You're going to have 6 plus n unknowns. So how to solve this? Whether it is solvable? Number of equations and number of unknowns are not matching. Number of equations is less than the number of unknowns, so we will not be able to solve it. So what can we do? We have to remove one unknown. Which unknown can be removed? Of this, I can assume density to be constant. Then it becomes an incompressible flow. I can assume density to be constant. I can remove it. So if I'm going to remove density, then I end up with 5 plus n equations and 5 plus n unknowns. That's one method. Or if I can't remove density, then I have to include the equation of state, which will be relating density with pressure and temperature. So I get with one more equation. So I end up with 6 plus n equations with 6 plus n unknowns. So this is what is being done in Fluent. So when you're going to go with Fluent, if you want to solve for compressible flows, gas dynamical flows, supersonic flows, what you do is, in material property, there will be an option of density. We will be changing it to ideal gas. The reason is, density is going to vary from point to point, and then that must be calculated. So that is the reason you have to set it as ideal gas. We cannot take a constant density and then solve for a supersonic flow. If you're going to do that, the number of equations, the number of unknowns are not going to match. The results will be not correct. So Okay, so that's about the material properties. So now comes the turbulence. The major problem in CFD is because of this particular phenomenon, turbulent flows. If we had a laminar flow, life would be, much more easier. Turbulent flows is going to be a problem for us. So now when you're going to look at turbulent flows, so any flow, inherently, naturally occurring flows will be turbulent in nature. Unless we are going to have controlled experiments in our labs, we will not be seeing laminar flows. So that being said, so what are these turbulent flows? So the flow which is going to be coming out of a jet or maybe a normal wick which is burning. What will happen is as it moves away, it starts to move further away from the steam lines. So it's not going to move in layers. So now this, as it is going to be rotating, it will be creating a lot of eddies. So this rotation eddies is going to be of different sizes. They are going to be large, small. So the thing is, what generally happens is the energy will be distributed among these eddies. The thing is, smaller eddies can join together to form a medium size one, and then medium size one can merge to get form a larger one. Larger one can destroy into smaller ones. So all these things will be generating entropy. So now this being said, turbulent flows, we are going to have different turbulent scales. From integral length scale, that will be the largest eddy can be on almost the same size of that of your phenomenon, the diameter of the pipe. And then Taylor scales, the intermediate ones. And then you have the Kolmogorov scale, the smallest one. Okay. So the Kolmogorov scale eddies knew only two things. Either they can break further down and be dissipated as heat, or they can accumulate together and then become a Taylor scale. So the thing is that those small eddies doesn't know whether they are generated from flow inside a pipe, or flow coming out of a jet, or flow over a flat plate. They don't know that. All they know is they can either dissipate as heat or they can accumulate together and then form a Taylor scale. This is going to be crucial when we are going to use the turbulent scales. So why is turbulence very difficult? So the thing is, based on the size of the eddy, we'll be calling this one. So you have the wave number is going to be given by 2 pi by lambda, the wavelength of eddy. So when you're going to have higher wave number, this will be the smaller eddy, which will be mainly concentrating on energy dissipation. And the larger eddies will be depending on the problem. So the larger eddies behavior is going to be different for flow over a flat plate, or flow inside a pipe, or flow of a jet. So why is turbulence more difficult for us? So when you're going to say velocity measurement, so because of this up and down movement, velocity is not going to be a constant. It's going to be varying with respect to time. So when I'm going to put the velocity probe at any particular point in a turbulent flow, I will not be getting a constant value. In laminar flow, if I'm going to take a point, it will give 10 meters per second. It will going to be always 10 meters per second as long as I'm going to do it. But in turbulent flows, it will be fluctuating up and down. It's going to be very difficult to get an accurate value. And the worst cases, even it will not be like this, where you can average it out over a time. The average itself can be a function of time. So when a rolling up of vortices is being happening behind a bluff body or square or cylinder, you can have rolling up in clockwise direction and then in the anti-clockwise direction. So velocity itself will be fluctuating over time. So now comes the difficulty. So now the major difficulty is if I want to capture this velocity fluctuation, my computational size, the mesh size must be really small, and then I must take the time size also to be really small. I must look in micrometers and then time size of nanoseconds. So if I'm going to say I want to do that for an aircraft, which is going to be, or any by test section, this is going to be of 1 meter in long. And then the test experiment will be taking for something like 20 minutes. The time taken to complete the simulation is going to be really difficult. So we will not be able to do that. So that comes the problem. So now, okay, so then people started to look into it. Okay, so they are saying that velocity is going to be an average velocity and then fluctuating velocity. Okay, so now what we can do with this? Okay, so now if we are going to look at our equation, and then if you are going to replace wherever you're having velocity with average and fluctuation, then it becomes like this. Equations are going to become much more bigger and complex. So similarly, we have momentum balance. And so we have average and velocity and fluctuation. And then, so now comes the problem. So previously we had U, V, and W. Now we have U bar, U prime, V bar, V prime, W bar, and W prime. So that means we are going to have 3 additional unknowns, but the number of equations is not changing. So this becomes the problem of turbulent flow. So people were thinking of how to solve for this because discretization into smaller domain was not feasible. So they have to think of something else. And then came Reynolds average Navier-Stokes equation. He said that, okay, so now let's take the average. Double bar will be giving you the average itself. Average of fluctuations is going to go to 0. But product, and it's going to be fluctuation of product, and then if you're going to take an average, that is not going to be equal to 0. And our differential equations can be still operated on averages. So when you're going to do this, what will happen is you have U bar plus U prime, isn't it? So that what U prime will be going to 0, so you'll end up with only U bar. Similarly, V prime goes to 0, V prime bar goes to 0, you end up with only V bar. W prime bar goes to 0, you end up with only W bar. Okay, so for continuity is good. But momentum, okay, here you have U bar, V bar, U bar, W bar, U bar. But on this side, you end up with U prime, U prime, U prime, V prime, and U prime, W prime. Then when you have U prime and U bar, that goes to 0. And similarly, when you have U bar and U prime here, that also goes to 0. But you are ending up with this terms. Okay, so now this looks somewhat easier that I have reduced the number of terms, but still I don't know U prime, V prime, and W prime. So how to solve for it? Then Bose came up with an approximation. He said that this U prime and U prime into rho is having the same unit as that of a stress. The units are same. So we can say this is going to be equal to mu T into this one. So mu is not the viscosity of the fluid, but viscosity of the turbulence. So mu, if it was mu, we know that because that's going to be a property. We know mu of water, we know mu of air. That's a property, we can directly give it. But we don't know mu T. So now when you're going to replace U prime as mu T, U bar, the equations are going to be reduced. Okay, so the equations are going to be reduced like this. So you can see that there is no U prime, V prime, W prime in my equation at all. So that means I'm going to end up with the same number of 6 plus n equations and 6 plus n unknowns. Any doubts, queries? But life is not that much simple. We have a mu T here. What is this mu T? Mu T is a function of U prime, V prime that is not property of the fluid at all. So same water at different velocities can give different mu T's. So that means you must have a method to calculate the mu T. Mu T is a property which is going to depend on velocity. So if you're going to calculate velocity, you must find mu T. So that means you are going to have additional unknown. So you are not going to have 6 plus n, we are going to have 7 plus n. What we have done is we have converted 9 plus n into an 7 plus n problem. So mu T is a turbulent viscosity is going to be a flow parameter. So now comes mu T is not going to be a property of the fluid which you can measure experimentally and get the value, but it's going to be a flow property. So we have to model it. So we are going to make some assumptions and then we are going to solve for it and then get the value for mu T. That if it is not matching with the experimental results, our answers are going to be wrong. So we have to be careful when you are going to choose which models you have to choose for your mu T. So now, okay, if we don't want to model this, I'm saying that I can go with very small measures and very small time step size, then I'll be calling it as a direct numerical simulation. You will be requiring around 1 million of cells in a size of around 1 inch cross 1 inch cross 1 inch to look at how the flow is developing. So that is a general kind of numbers they are looking at it. So People are still doing this. DNS has been done to validate the commercial codes, and people who are going to work on coding, they will be using DNS as a reference. Or we can go with the Reynolds average. You model the turbulence. We take U bar, we are going to say we'll solve for U bar, and then we will solve another method for mu t. This U bar, and then we are going to do some assumption calculation for U prime. When you're going to add together, you're going to get the velocity. If our assumptions are wrong, the final answer also going to be wrong. So we have to be careful with our modeling. Or we have the large eddy simulation lying in between, where we will model the smaller eddies and solve the larger eddies. So why we are saying modeling of smaller eddies? As we looked at it, smaller eddies have two phenomena. Either they can dissipate as heat or they can accumulate together and form a larger eddy. So if you are able to differentiate the smaller and larger eddies, we can do this. This will be giving a slightly better results than RANS. So LES is going to be a turbulence option available if you are going to go with Fluent. Okay, so now turbulence can be modeled in various methods. You can have a simple one equation model. Mu t is going to be equal to some constant into rho into V into L. So at a particular cell, I calculate the velocity and a length scale. And then I'm going to multiply those two. And then I calculate the velocity at mu t at that particular cell. With that, I find the mu prime at that particular cell. And with that, I find the value of U at that particular cell. So this is one equation model. Or you can have two equation model. We can have turbulent kinetic energy K and dissipation of kinetic energy epsilon. We can use that to get the length scale and velocity scale and then substitute in this equation. So now we are having additional parameters K and epsilon coming into picture. So that means you must solve for this K at every cell. K coming in minus K going out plus K generated minus K destroyed is going to be equal to the rate of change of K in that particular cell. This is what our equations are going to be coming. Or we can have omega. Omega is nothing but epsilon by K. So depending on the fluid dimensional problem, you'll be having different kinds of models. We can have 7 equation model where you model rho U prime, U prime, V prime, the diagonal matrices. Okay. So now when we are going to look at a cell, so this will be the turbulence modeling. We can look in Fluent. There will be options of various turbulence models. So you must choose which is your model correctly. Some models are specifically for flow across cylinders. Some models are for flow inside pipes. So you must choose those correctly. Okay, so now in a finite, so that is one section in the Fluent. We can find turbulence modeling. We'll look at that back in later, a little bit later. So when you're going to have cells like this, generally what we'll be dividing is, we'll call this one as an present cell, and towards the right is going to be east and left is going to be west. If you're going to have a top and bottom, we have north and south. So you can have multiple cells are going to be surrounding a particular cell. So, and the walls will be given in lowercase, east wall and west wall. So now any property is going to be changing. So the thing is, in a finite volume method, you'll write this like this. You'll have a convection term and diffusion term. So all our equations can be written in form of like this. If you're going to say heat conduction, Q is equal to K dt square by dx, gamma becomes K. If you are going to go with the Navier-Stokes equation, you have phi is U, then gamma is changed as mu. So you can write any equation. This is a general form of equation. So you're going to have a convection term and a diffusion term. So when you're going to expand it, you'll be getting, so go by dou x can be written as east wall minus west wall. That's going to be the value at the property. And similarly, here you can write it and how much it's going to diffuse. Again, if you're going to go it further, you'll be differentiating this with the change in property over the distance. Why we are going to go with this? So now What is the values are going to be stored in the cell centers. I'm going to be calculating the pressure, temperature, velocity at the cell centers. So now how to determine the property at the wall? For that, we can have multiple methods. We'll be calling it as, this will be termed as flux, and this will be the diffusion term. We can take the property at the wall as average of the cells. That will be called a central differencing. Or you can take the wall property before. You can have a forward differencing or upwind differencing. So generally we can go with the Pecklet number. I think this will be available in standard CFD books like Malasekara. When to choose which? So if we are going to say we are going to have a flow, and flow is from left to right. So this property, the property here, how much is going to be depending on the property here and property here? So if you are going to have really supersonic flows, then you will be depending on property only upstream, above the wall. You're not going to be depending much on the downstream points. So that means so there will be schemes like quadratic upwind, quick scheme. So these are the additional schemes which you'll be selecting when you're going to solve in Fluent or any software. So you must know what is the schemes and what is the reason for selecting that particular scheme. So if you're going to have a normal diffusion problem, you can go with central differencing. If you are going to have high-speed flows, generally you'll be going for quick schemes. So this also must be selected when you're going to choose for your Fluent. So this is another method. You can take 3 walls, 3 points upstream, and then solve it. Okay. And one more thing which we'll be using is when you're going to go with then pressure and velocity coupling. So when you're going to have flows, the thing is, this came up with an idea when people were thinking that, okay, so now we are saying that we are going to be putting pressure and velocity at some particular points, the cell, and then you're going to calculate it. What if we are going to get an unphysical phenomenon? That is, the point is going to have a pressure of 50 Pascal, and before on either side, it's going to have a pressure of 100 Pascal. That will be called a staggered grid. So when you're going to have a staggered grid, the pressure difference, P minus P, will give you a 0 value. That means pressure velocity is not going to be there. So if that is the case, but still velocity is there physically. So how to overcome this? So for that, they came up with a staggered grid, and then so what they did was, so their methodology was developed. We have to first assume a value for P, and then solve the Navier-Stokes equation, and then calculate the variation, and then calculate substitute in continuity equation, and then calculate P prime, and then adjust, solve for Navier-Stokes equation again. And then you have to calculate the actual pressure velocities, whether the solution is converged. If it is converged, you can go to the next step, or you have to reassume the value of P. So this method will be called as a simple method or semi-implicit method for pressure linked equation. So when you're going to have pressure and velocity have to be solved, you have to choose that particular methods. We can have various methods. We can have simple, simplex, simpler, piezo. So when you're going to go for Fluent, you must look at which methods to choose. Please look at the background equation for the corresponding method, because we cannot just, there are methods related for some particular problems. So once you know the physical physics of the problem, we have to choose the corresponding method. Okay. So now again we have another one method. When you're going to go with time step, we can depend on any property. We can solve by depending on a property at time delta t at a particular point p. Can be depending on the previous time step that will be explicitly known, or it can depend on the current time step. Then it will be going for an implicit scheme. So both is going to have its own advantages and disadvantages. So when people are going for codings, they will be worried about explicit and implicit, but commercial software will be having the methods to go with an implicit scheme much more faster. Okay, so one thing which you have to be careful when you're going to go for Fluent or going to go before Fluent is you're going to be a mesh. So now when you're going to take a geometry and then if you're going to divide into multiple parts, that will be the grids. And so to make sure our solutions are perfect, generally what we will do is we will increase the grid size in the X and Y axis. We will be doubling the grid. And then when the solution is not improving with the grid, we call it as a grid independent study. But apart from grid independent study, we can also do a grid refinement study. Grid refinement, the thing is, knowing the physics, you know at what points you are going to be crucial for you. So if you are going to have a burner, so that means just exit of the burner will be having all the combustion taking place. So that must be refined for fine. So the other regions can be of course. So that kind of study you can implement it before you are going to go with Fluent. That will be helping you a lot. We'll look at an example of this. And grids can be hexagonal, quadrilateral, or triangular and tet. We will be able to work on everything. But when you're going to have an sphere, how to mesh this? You're going to give mesh, automatically Fluent will mesh it. But you can do some methods to improve the quality of mesh. When you're going to have, you can have control over mesh if you're going to do it. So errors in meshing, common errors. Orthogonality, skewness. Orthogonality is going to be at 90 degree. Skewness is going to be the line connecting the cell centers. How much it is going to be deviating from the main flow. So this is a skewed element. Aspect ratio, length to breadth ratio. We cannot have a cells like this for your simulations. So cells must be almost same. Because if you're going to have cells like this, then the delta X distance between two cell centers will be different. And then it can create some diffusion problems. Okay, so now let's take a simple example of flow over a square cylinder. So fluid is going to come from the left and then it's going to leave away from the right. So I'm having a square cylinder of 10 mm cross 10 mm placed in the center of this domain. So we can air is coming at a velocity of 1 meter per second at temperature of 300 Kelvin. So it's going to go out. So I can make the mesh, I can make the geometry in workbench or as a Ansys workbench. I have made this in space time. You have to draw the two rectangles and then subtract this. So you get a shape like this. For first timers, Fluent is going to work on fluid. So you have to model the fluid and then you can have the solid as boundaries. So when you're going to talk of pipe flow, we must model the water inside the pipe and not the thickness of the pipe. That can consider unless you're going to consider for heat transfer between the pipes, those kind of problems. So now if you're going to ask the Fluent to do a machine, this is what it gives. So the thing is, you can see that this mesh is not very smooth. The thing is, I'm having a triangle element here, and then I don't like this mesh because it's not uniform. But when I'm going to say that an option of mesh controls have in Fluent, you can specify the number of elements. And I'm going to say I'm going to go with a phase meshing with 1 mm mesh. Now I have meshed everything with 1 mm. You can find that this mesh is comparatively better. So it is uniform. Every cell is of size of 1 millimeter, uniform square meshes. Or if I'm going to go with 0.5, I get it more fine. So again, it's going to be 0.5 everywhere. So I'm having a better mesh. But the main thing is whether I want 0.5 mesh at this particular point. Fluid is going to come into this. I'm not interested in this. I'm mainly interested in how the fluid is going to be rotating in this particular region. So that means in this domain, my region of interest is going to be this one. So I want a fine mesh here and a coarse mesh around it. So how to do that? We have to divide into multiple square segments, and then we can do that. So now we can see that the mesh is fine here. I have given a 0.5 mm mesh in this particular region, and then 1 mm mesh in this region. So what is the advantage of doing this? Why not allow Fluent to do everything on its own? So this was my first mesh with the 1 mm. The cell count was 4,957. When I reduced the mesh size, 0.5 mm, I got around 19,000 cells. But when I took the control, I got around 15,000 cells. So that means I have reduced the cell count by 5,000. So where is going to be helpful to me? So now I'm having 5,000 less points, and then the computer will be able to do it solve the results in a faster manner. So instead of taking something like if you're going to say it will take 1 hour to complete this, you'll be getting the results within 45 minutes. So that's the advantage of having an grid refinement. So why I'm going to go with the term of grid refinement? So if I'm having 5 points and I'm getting a curve like this, when you're going to do a grid independent study, what you're going to do is you're going to increase it into 10 points. And then you're getting a curve like this. So now here there's a deviation in the results. Next, what you do is you increase it into 20 points. Then you find that there's no deviation between 10 points and 20 points. So we can continue with the results with the 10 points mesh itself. But in reality, if you're going to have an 7-point mesh, what happens is you'll be getting the same results, but at a faster method. So this is the advantage of grid refinement. So wherever there's going to be gradient, I'm putting more number of cells, and where there is not much gradient, I'm going to go with the coarser mesh itself. To know where there's going to be gradient or not, you must understand the physics of the problem. So if you're going to have a flow past cylinder, then you're going to be interested in what is the dynamics happening after the cylinder. If you're going to be interested in supersonic flows, where the shocks are going to happen, that is when you're thinking of interest. So depending on the problem, you have to find a region of interest and put more cells in that region. That will help you in getting your solution faster. Okay. So that is about meshing when you're going to go with Fluent. So we have looked at the turbulence modeling and then other methods of selecting it. You must either go with the semi-implicit method or PSO methods, or you can go with the different methods we can choose. So apart from this, one more thing which you have to remember is, so when we are solving for a differential equation, we are solving for ordinary differential equation, but computers cannot solve for the ordinary differential equation. So what we are going to do is we're going to convert this ODEs or PDEs into algebraic equation. So what we are going to do is, so if we are going to do it in Taylor series expansion, we will be getting dou u by dou x as u of can be written as u of I plus 1 minus u of I by del x and other terms. And or you can write in I minus u I minus 1, or you can write it as I plus 1 minus I minus 1. So we can have forward differencing, backward differencing, central differencing. So now if you look at it, what we are going to do is we are going to truncate it here. We are going to neglect all the terms that will be present here. We are going to say dou u by dou x is nothing but u of I plus 1 minus u of I by del x. Or dou u by dou x is u of I plus 1 minus u of I minus 1 by 2 del x. So what is this is going to be significant for us? So when I'm going to leave off this, I'm converting the ordinary differential or partial differential equation into a set of algebraic equations. I'm leaving off some terms here. So that is going to be creating, can you go back to the previous slide? Yes. So that's going to be creating some errors. So now if you look at the magnitude of errors, we are saying, let's say that we are going to have a delta x of 0.1. So that means this error is going to have a magnitude of 0.1. This is going to have an error of magnitude of 0.1. This will have an error of 0.01. So that means there's going to be more advantage. The error is going to be lesser when I'm going to go for central difference. So this is what we'll be again choosing in Fluent. We can go for different methods. We can go with which method to choose. So now let's take a simple heat conduction problem. So we are having the equation as d square T by dx square is equal to 0. and I'm having a rod. I want to determine the temperature at different locations in this rod. So I'm going to write the equation, d square T by dx square. So I write in terms of Taylor series, and I'm going to go with second order, so central. So it will be much more better. So now I can write d square T by dx square is equal to this term. Then I'm going to truncate it here. So this is my equation. D square T by dx square is equal to 0. So I can multiply by delta x square. So I end up with this. So when I is equal to 1, okay, we don't have the equation because we are not going to have I minus 1. We are having only 4 points. Can you go back one slide? Previous slide. Please. Yes. So we are having 4 points. So that means I can't substitute I is equal to 1. I must substitute I is equal to 2 and 3. Next slides. Yes. So now I end up with 2 equations. Okay. So I have 2 equations. What are my unknowns? How many unknowns I'm having? Yes. I don't know the value of T1, T2, T3, and T4. So that means that I'm going to have 4 unknowns. How to solve this? Whether we can solve this kind of problem? So this problem cannot be solved unless we reduce the number of unknowns. So what we are going to do is we will be taking the boundary conditions. So even in Fluent, we are going to do the same thing. We are going to put the value for all the parameters in the boundaries. That will be the boundary conditions. You can have the boundary conditions at Dirichlet or Neumann boundary conditions. Here I am giving the temperature directly. T1 is 400 and T4 is 300. Or I can give in terms of dou T by dou X. Or I can give in terms of Q, where Q can be written as H into T minus T infinity. So in Fluent, if I'm going to do it, we can have different methods. We can have mass flow inlet. When you're going to give mass flow inlet, you'll be giving the mass flow rate. And then if you're going to say area density is constant, you have given a value for density. Mass flow rate is going to be given as rho AV. Density is known. Area is going to be obtained from the mesh geometry. And then you are giving the velocity at all the points. Generally, along with mass flow inlet, sometimes they will be also giving the temperature inlet values. So we are giving values for pressure, temperature, velocity, turbulent kinetic energy, epsilon, whatever models you are going to do, we will be giving all those values at all the boundaries. Without that, the system will not be able to solve it. If you don't know the values at the boundaries, again, we will not be able to solve the system. So you must know the values at the boundaries, or you must extend the boundaries till the locally value of the value. So if you're going to have a pipe flow, and then some jet water or fluid air is going to enter into the pipe, you know that pressure and velocity. It's going to come out, but you don't know the exit values. But what you know is it's going to be exited into an atmosphere. You know the atmospheric pressure. That means you must model the atmosphere and then give that value. Then only you will be able to calculate the exit pressure of your pipe current. So otherwise, if you are going to give some value at the exit of the pipe, it will do some calculations, and then our answers will be wrong. If you are going to change for 300 to 200, the answers which you are going to get here is going to be different. So you must be careful with the boundary conditions when you are going to specify. So we are having 2 equations, 2 unknowns. We can substitute in the form of matrix and then solve. But again, life is not that much simple. Computers, yes, matrix inverse can be obtained in a single go. Be in the previous stage. Now this is a 2 cross 2 matrix. If I'm going to put 10 points, then it becomes a 10 cross 10 matrix. This is 1-dimensional heat transfer. If I'm going to go for 2-dimensional, then it becomes a 100 cross 100 matrix. To find an A inverse of 100 cross 100 matrix, it will be very difficult for the computer to do. So computers are not going to go for matrix inversions, but we'll be doing something else. What we are going to do? We are going to rewrite the equations like this. T2 is going to be equal to 400 plus T3 by 2. T3 is 300 plus T2 by 2. Something is on chat box. 1 minute. Yes.
Chat box and what again?
Any messages, new messages? I think, okay, I think that it was a question which I asked, whether it's solvable. Okay. Thank you. Okay. So now once you have made like this, what we can do is we can assume a value for the temperature at the intermediate points. So if I'm going to say I'm going to have a rod with 400 at one end and 300 at the other end, what temperature can be at the middle? Any guesses? I'm having a rod, 400 at one end and 300 at the other end. What is the temperature at the middle? Yes. Any guesses? Huh? Average. Average. You can take an average. You can assume the temperature to be 350. So that is going to be your initial conditions. Even in Fluent, we'll do the same thing. So we'll initialize the solution. We'll set the temperature, pressure, velocity, everything for every point, and then you start from. So once you have initialized it, what we are going to do is we are going to substitute T2 is equal to 350 and T3 is equal to 350 in these two equations. So our first iteration is T2 is 350, T3 is 350. So 400 plus 350 by 2. Okay, so what is 400 plus 350 by 2? That's the first equation. 375. 300 plus 350 by 2? 325. So that's where we'll be moving to the. And click on next one. What time? Yes. So now you go to 375 and 325. Next, what you do is you assume T2 is 375. 300 plus 375 by 2. You go to 362.5. Here 325 plus 400, 337. So we'll be going on substituting these values again and again. So what happens is, please go on. Yes. So now towards the 8, you can see that I have reached 366, 366, 366. It's almost consistent. So then what I'm going to say is, yes. So now this is the value, 366 and 333. So this is what Fluent is doing. It's going to do in terms of iterative method, the stepwise iteration method is going to be done. And then it's going to be showing you the final result. If we are stopping in between here at the fourth iteration, our value will be 365 and 334. Yes, for this case, it's not varying much, but in real life, the solution may not be as good as the physical solution. Okay. So now this difference between the previous time step and this time step will be called as a residual. So Fluent generally what it does is it checks whether the residual is going to be decreasing. If the residuals are decreasing and then it comes below something like 10 power minus 6 or minus 7, it can say the solution is converged. But the problem with this is, if you look in gas dynamics, we can have the same, for the given A by A star, there can be two solutions. One will be subsonic solution, other will be supersonic solution. The computer doesn't know whether it reaches a subsonic solution or supersonic solution. So that means you must be careful with the physical concentrations also. If you have made some error, it may say the solution is converged, but you must look at whether the values are really matching with what is being done, experimentally observed, or what you are expecting. So you must be careful with that, because we are going to look at only residuals. Residuals is just difference of two numbers, and it can be misleading sometimes. I'll show you an example later. So this was when I took the case into Fluent, it was taken. I have to specify the boundary operating conditions. I have set that as 0, and then in boundary conditions, I set the value for velocity and pressure. And I am assuming an isothermal condition, energy is turned off, so temperature is going to be constant throughout. If temperature is varying, here in this thermal tab, we will be including the temperature at the inlet. Since my flow was coming towards around Reynolds number around 3000, I took it to be turbulent flow, and I'm giving the value for turbulent intensity and hydraulic ratio. So the thing is, this will calculate K and epsilon, and that also will be coming into your equations. And here is where we'll be giving with the different methods: second order upwind, least square, simple, coupled equations, piezo. You can various kinds of solution methods can be prescribed. Please look at the standard methods which is prescribed for particular cases, and then you can install those particular methods. Otherwise, you are going to go with default. The chances are there the errors will be accumulated, and then you are getting a different answers. And this is going to be the solution controls. How much amount of the iterations is going to be depending on the previous time step. That way, you can have it here. You can reduce it if it's diverging. And this is my initial equations which are going to solve is for flow and turbulence. And this is my initialization. I have set the values for pressure as 101325, velocity as 1, y velocity is 0, k and epsilon, and then I'm going to start the iterations. So we looked at the residuals, and in this case, our residuals are decreasing. But if you look in my case, the residuals is almost constant. The reason being, I gave an initial guess very close to the final solution, so the residuals are not improving further. So how to check whether I have got the solution? We can look at contours. I have got a contour like this after something like 5,000 iterations, but I know this is not correct. Please see. I know this is not correct because the contours should actually roll here and then it should be covered. So that is the significance of flow over a cylinder. So that means I must run it for a longer period of time. So when you're going to depend on Fluent to allow it to solution to converge, we must check whether it is physically correct. So we must validate our code with an already existing experimental result to check whether we have reached the point where the solution is acceptable. So, okay. So whether this is how Ansys was working on it, I wanted to give a new method for solving. So now that's going to, we'll be doing it. So now we are interested in calculating the temperature at this particular point. Okay. So I will be requiring your help, those are in online and offline. So what I want you to do is a small exercise. We are going to do and whether you'll be able to solve this without going through this all this complex mathematical equations. We'll do a simple thing, will be tossing a coin. You're going to toss a coin, and if you're going to get heads, please, everybody, please participate. We'll be requiring your results to find the final solution. So when you're going to get a head, you have to move towards the right. When you're going to get a tail, you have to move towards the left. Okay? So now you have to repeat it again till you reach a boundary. And then you must note the temperature at that particular boundary. So we are going to start at point 2. You're going to toss a coin. If you get heads, you move here. Then you toss a coin. If you get heads, you move towards the right further. Or if you're going to get a tail, you come back to this point. And then you have to toss a coin again. You must repeat the coin toss unless you reach any one boundary. Okay. So what is the participation list? I think around 60 are there. So that will be a good sample size. So we can just check which boundary we are reaching. So I'm saying that this is going to be a temperature of 400 Kelvin. This is going to be a temperature of 300 Kelvin. So I want you to please take part in the activity, toss your coins, and then mention which boundaries you are reaching. And those are in online, please give your results in the chat box. Participants are. Let's finish it. That's a random event. We are looking at a random event. It can be either
மாதிரி போடுவாங்க. இது அது இது அது மாறி மாறி வரும்னு சொல்ல முடியாது. சொல்லுங்க, பெண் uncertainty will be high.
Definitely high, but the thing is, huh? Reached one. Okay, so we have a 400, 1, and others. We want more number of samples. That's what. Everybody will participate. Okay, start from point 2. If you're going to get a tail, you reach this point. If you're going to get a head, you come here. If you're going to, you must toss a coin again. If you're going to head, you reach here, or you are going to come back here. Again, you toss a coin. Tossing of a coin, I'm just going with a random event.
Top three, we got two answers. We got three times of iteration.
2 for 400 and 1 for 300.
Yeah.
Okay. So that's offline.
Three times.
Okay, that's okay. That's okay. I'm not interested in that. The thing is, I'm getting 400, 400, 300. Similarly, I'm looking for online participants. Please give your answers in the chat box.
400.
Okay, you have got and
Out of 6, 400.
out of 6, you have all 6 are 400.
Out of 10, sir.
Out of 10, how many?
400.
Okay.
4.
Okay, you don't think you just your result was 2?
2, 400, 1, 3.
So
6, 400.
okay, 6. Try 400 and put 6. 400 is 6 in your case, and 2 in that case. So 6 plus 2. Okay, and 300 is
300 is 4.
300 is 4, and 1. 4 plus 1. Let's see whether online participants don't know whether it was audible or taking part in this activity. Whether the chat box is open. Chat box is open. Anyone has given messages already, or okay, 2 new messages. Yes. Yes, please take part in the activity and give your answers. 300 or 400. Okay, one more for 400. Add 1 for 400.
Two 400, one 300.
You want more samples? And still in random event between the 2 points, that's not that highly possible. I have to reach a boundary somehow. 400 5 times, 300 5 times. Oh. So add 5 for both. Okay. Five times both is yeah, I think you're having a perfect coin to go heads and tails uniformly. Okay. Yes. Can we no? Okay, I think no further responses. So how many 400 we have got totally? Huh? 13 400 and 300 10. Okay, so what is 13 into 400 plus 10 into 300 divided by 23? 10 into 300 divided by 23.
356.52.
356.52. And I think if you remember, please go back a few slides. The temperature here, when we solved it by iterative method.
333.
No, I think I changed the temperatures. 400 and 300, isn't it? Oh, I think I changed it. Okay. Okay, go back to that temperature. Yes, further up.
23.
Further up. Yes. Towards 400, you have a temperature of around 366.65, and your values are around, the value which you have got is 356, 10 degrees difference. So if you have more number of samples, we'll get the exact value. And please go to that. This method is actually called as a Monte Carlo method, where now the new technology is new research is being concentrated on this one, where you take a particular point and then you develop a code to solve for that particular point. What is the major advantage of this? We didn't use our equation at all. D square T by dx square is not being used at all. We didn't, so the thing is, and but we have to specify the value. So now if this was an temperature is known, you can give like this. But if it's an insulated boundary, how to do that? Then what you have to do is you have to consider that wall to be a blocked one. So this method comes from the term Monte Carlo, which is going to have an port town, which is going to be having a lot of casinos. So the thing is, what you're going to do is you're going to randomly walk into one casino. So you randomly walk in the road. That's the major idea. You are going to go with a random generator. Coin toss is going to be a random generator. You can either get heads or get a tail. You are not sure whether it will be always getting a head or always getting a tail. So now, if you're going to move in 2-dimension, then you have to have a dice which is going to be having north, east, west, and south. You have to move in random direction till you reach a boundary. So once you have done that, you have to repeat it. Maybe now we have done for 20 times. If you're going to do it for 1,000 times, the answer will be much higher. So now the major advantage of this method is it will be able to give you the parameters at one particular point. You need not solve the entire domain. You need not go with the mesh at all. I'm interested in pressure at this particular point. How to solve it? You can develop a code for Monte Carlo method. But the catch is you must know how to give the boundary conditions. If you know all the boundaries, then the problem is straightforward. But if you don't know the boundaries are going to be like convective boundaries. Or if you're going to have an insulator, or if you're going to have an radiation boundary. So that is going to be slightly tricky to give when you're going to go for a Monte Carlo method. And one more advantage of Monte Carlo method is you'll be able to achieve parallelization like anything. So now when you're going to go with the Fluent so far, now we'll be dividing it into multiple segments. And then if you are going to have a very large domain, what system will do is it will divide it into 8 parts. And then each part will be given to one core. And then from inlet to the first segment, it will be solving. And then that result will be given to the next core. So when you're going to go with more number of points, more number of divisions, what happens is the time taken for information to pass from one core to other will become higher. And it will be causing a total time will be increased. But this is not, each point can be solving on its own. It doesn't depend on the result on the next point at all. The nearing points is not going to be depending at all. You have 1,000 people. You can ask them to solve for temperature at 2 alone. Another 1,000 people. You can ask them to solve for temperature at 3 alone. But in iterative methods, temperature 2 is going to depend on temperature 3 and temperature 3 is going to depend on temperature 2. Unless temperature 2 is solved, temperature 3 cannot be solved. You have to wait for it. That waiting time is going to be reduced in Monte Carlo method. It's going to be the new age where people are looking at research funding. So anybody is interested, you can go into this one. But the thing is, we have to go with the working with codes, and that's not going to be available in the commercial software. Okay, so these are a few analysis and methods of giving of results done by my research scholars. So it's going to be a heat transfer problem. You can show streamline plots. And as I mentioned in the beginning of the slide, CFD was considered as colorful fluid dynamics. So generally my results will not have any colors unless it's not required. So this is going to be streamline plots. You can achieve it. We can remove the filled option in contours. You'll be getting patterns like this. You'll be getting only the contours. That also will be giving you a lot of information. Apart from the color images which can give, you can see that the vertices are being rolled at these locations. Those informations you can look into it, and then maybe you can look at the distance between the vertices and try to do some analysis on that. Those kinds of things can be done. The size of the vertex can be determined. So you can use analysis, additional analysis from the same results. And it's going to be an ejector refrigeration problem done by another research scholar. So this is going to be a variation of shocks. Location of shocks can be seen. How to interpret it when you're going supersonic flow is going to be coming here and subsonic flow is coming here. How they are going to mix it? There's going to be shear layer being developed. Those kinds of things we can obtain in the CFD. And our classical bluff body problem, as I mentioned, this is the kind of result I'm going to be expecting. But when you're going to get a constant shape, that means you're indicating that you have to run the simulation for longer period of time. So that must be careful. So, and this was done in CD Adapter. Apart from Ansys Fluent, they have multiple options. You can look into it. CD Adapter is there. OpenFOAM is available. OpenFOAM, the difficulty is we have to write our own codes. So if the existing, the thing is, it's not going to be graphical user interface, is going to be very poor. So you have to go with the coding kind of thing. You must get the dimensions and then specify. So the thing is, if you're going to give in Fluent, if you're going to give mass flow inlet, you can go to that boundary and then change it into mass flow inlet, and then you give the pressure, velocity, you give the velocity and temperature, pressure values. Here, there will be a file called P. You have to go to that. And then in that file, there will be a line setting inlet. Then in that, you have to give the you must specify whether it's going to be a Dirichlet boundary condition or a Newman boundary condition. If it's going to be, then you go to another one file and then give the value of pressure there. So that's how you'll be more of coding kind of thing. But OpenFOAM, the major advantage is it's free. You can download and run on your own. No need to worry about it. It has the same capacity as that of Fluent. But the only thing is, in Fluent, if I want to go from simple to simpler algorithm, all I have to do is I have to go and change from in the drop-down box from simple, I can change it to simpler. That cannot be done. SST K omega to K epsilon model, single click will do it. Here, you must go and get the K file folder, epsilon file folder, and then put it in your directory and then change the values accordingly. So that's the major difficulty of OpenFOAM, but still it's a good tool to work on. And again, this is going to be in the Start CD. Start CD is going to work with, depending on the kind of problems, you can choose different kinds of solvers. If you're going to go with the IC engines, Start CD is really helpful. You can look into that. This was one result which was given. And I think I'm towards the end of my presentation. Most of my references, images, equations have been taken from these two books. CFD by John Anderson and CFD by Westig and Malasegra's classical books. You can look into those things for much further readings. So now it's open for any queries.
Actually, I'm having a query.
Yes.
With machine time, we are using with that. You have to select the type of machine. There in CF Ansys Fluent, we are using a 16 version. There we are finding that the proximity and curvature option is there.
Okay.
When we are selecting, means it will take some months time. Whether
no, the thing is, when you're going to go with meshing, my guide used to say meshing is more of an art as of a science. The thing is, when you're going to ask proximity as curvature, all those things, when you're going to give it to the machine, it will do some mesh, but it will take longer time. So what you have to do is, generally you can divide. So now if you look in my case, I will divide my domain into smaller domains. So, and then I will always use the hard fixed dimensions. So the thing is, if this length is going to have 10 mm measures of 10 mm, 10 mm only is going to be there. Next length can be of different size. When you're going to have curvatures, we can accordingly, best option would be to draw another one curve slightly away from it and then match the mesh there and then proceed from there. So that will be much more easier. The thing is, you will spend more time to draw the geometry and less time for waiting for the mesh to be generated. And that also must go to Fluent. We have another one. If you are going to go with academic version of Fluent, we'll have another one problem with 5 lakh cells. We cannot go beyond that because after 5 lakh cells, it will say mesh will not be, it's not compatible with the solver. So then we have to come back. So, and one more thing, what we can do is, depending on the problem, we can try to do some modifications in the geometry itself. Whether you have to go for really 3-dimensional problem, or whether we can go with an axisymmetric modeling, or whether we can do a 2D analysis, those kinds of things we can look into.
More things selection process, that a simple method, and which one is best for heat exchanger?
Heat exchangers, you're saying heat exchangers, whether it's cross flow. Okay, generally, cross flow heat, counter flow heat exchanger. You can go with the heat exchangers, you're not going to go with the high speed flows, or whether you're going to go with high speed flows, supersonic flows.
No,
nanoflates and non. So that means you can go with the simple or simpler will be doing it. When you're going to go with the supersonic flows, then we can look in different kind of things. But normal heat exchanger, simple or simpler, will be able to solve it. And generally what we can do is we can choose the second order equations. There will be multiple second order equations. You can go with the second order equations. And that itself will be able to solve it. But the thing is, just allow the iterations to run a little bit longer. Otherwise, check whether with some standard results. So when you're going to take an initial heat exchanger, take a standard model available in the literature, and then check whether you're getting the same values without nanoflates or without pure fluids. So then what can you do is, we can be sure at when to stop the iterations. Otherwise, we'll not be knowing when to stop the iterations. So generally, you can allow the iterations to run. Maybe you can save it every 1,000 or 2,000, something like that, and then you can compare the results, how it is improving, whether it is improving or not. If it is not improving, you can take that itself. If it is improving, you can wait till it reaches what is reported in the literature. That's what the thing is. We are not looking at the residue, the iteration number which the literature says, but you must look at the exit parameters. Maybe temperature at the exit, some parameter if you are going to take, and if you are going to get the same value, till that you have to do it. We can't avoid it. But if your mesh is really better, you'll be getting it in a faster manner. That's the main thing. Yes. Yes. If one general doubt regarding CFD, what are the limitations and potential sources of error in CFD simulations? How can be mitigated and minimized? Okay. Drilling gaps. Okay. So now when you're going to talk of errors in CFD, you'll be having major 3 errors that is inherent of the nature of CFD itself. First thing is, we are going to convert the differential equation into algebraic equations. So that is going to be giving you that discretization error. And then we are going to truncate the Taylor series. So that will be giving the truncation error. And then depending on the system we are going to use, 32-bit or 64-bit, we will be rounding off to that number of digits. So that's going to be a round off error. So all these errors are going to be there in our CFD simulations in the first place. So now how to minimize it? Mitigation and minimization is going to be depending on how we are going to choose. The thing is, first, we must make sure we are choosing our equations correctly. That is, if it is a laminar flow and if you're going to go with K epsilon model, the system will still give the answer. So you must check whether the flow is laminar or turbulent before choosing that model. And like that, you must look at that first. And so that is the reason we'll be always going for the validation part. We will be taking, so before we are going to start any particular geometry, check whether the geometry is available in the literature, and then with what are the parameters they have measured. We must be able to get the same measurement values. But the limitation with which many students or UG students or even PG students will be getting is, if they are going to work in academic version, they will not be able to get the more than 5 lakh cells. In that sense, you will make some assumptions. If the geometry or experimental work was done was 3D, you will assume it to be 2D and then you will be doing it. In that sense, what will happen is the result will not improve. There will be some small deviation. So what you can do is you can test two cases and then check whether the results are going to be same between the deviation in the results is going to be same for both the cases. Then we can go with the same methodology. Okay. Drilling characteristics. Use in studying drilling characteristics. Okay, drilling characteristics is going to be an if you're going to look in tool removal and heat transfer in the tool, it's going to become much more complex. With the Fluent, it's going to be very difficult. We have separate tools for it because in Fluent, we are going to have a mesh which is going to be stationary. Now in drilling, the drill bit moves and also the other material is going to be removed off. So that's going to be a chipping of material. So to include all those things in Fluent is be very difficult. So you have other additional software to do that. You can use that one.